For decades, software engineering relied on deterministic logic. You provided an input, the system followed a hard-coded path, and it produced a predictable output. We are moving away from that rigid structure. Agentic AI replaces deterministic paths with probabilistic networks that operate independently. In an agentic workflow, an AI continuously perceives its environment, makes autonomous decisions based on internal logic, and coordinates multiple distinct steps to execute a complex task. Because the agent reasons in real time, it can approach the exact same problem using completely different execution paths on different runs. It might route through an internal database today and query an external vendor tomorrow, adjusting dynamically based on immediate feedback. This freedom to iterate autonomously allows the system to handle complexity that hard-coded logic cannot. However, introducing probabilistic uncertainty into a deterministic enterprise environment creates massive systemic risk. It is the reason why laboratory demonstrations of AI agents routinely fail when deployed into live enterprise production environments. This failure rate creates what researchers call the unreliability tax. This is the massive overhead in compute power, latency, and engineering hours required solely to mitigate the risk of the agent failing. Unconstrained agents fail in highly specific ways. They invent non-existent code libraries or get trapped in infinite loops, repeating the same failed action. They can accumulate so much conversational history that they overflow their context window, the maximum amount of text the model can process at once, and forget the original instruction entirely. But the most dangerous failure mode occurs when they execute tools using the wrong parameters. You cannot solve these flaws by simply routing prompts through a larger language model. The architecture itself is the bottleneck. Achieving 99% reliability in production means shifting focus away from model parameter counts and toward rigorous systems engineering. To build this enterprise stack, we start with a completely isolated language model. In this state, the model can reason, but it has no ability to retrieve live data or take action in the outside world. To move data beyond the model's internal weights, we implement a mechanism known as function calling. Instead of generating a conversational text response, the model outputs a structured JSON payload. JSON is a standard text format used to store and transport data between systems. This payload dictates precisely which tool the system should use, like looking up an invoice, and provides the exact arguments required to run the search. Function calling translates the model's abstract reasoning into deterministic execution. The AI is no longer just generating text, it is generating instructions for action. However, direct access allows an unpredictable model to execute commands against the production environment without a verification layer. To secure this communication, we introduce a tool gateway. This mandatory mediation layer intercepts the payload before execution can occur. It enforces schema validation to ensure the data is formatted correctly, and it applies role-based access control, or RBAC. RBAC is a security method that restricts system access strictly to verified user permissions. While function calling enables action, the tool gateway ensures the model cannot perform unauthorized actions. Once the agent is secured to take action, we hit an immediate trade-off between latency and accuracy. On complex multi-step tasks, the accuracy of a single SHA-Lilith model plateaus at roughly 60 to 70%. To push past that limit, engineers use an architectural pattern called reflection. Instead of generating a final output immediately, the agent acts as its own critic. It drops code, runs it through unit tests, evaluates the failure, and rewrites the code in a continuous loop. This improves accuracy, but it incurs a massive performance hit. A workflow that takes 800 milliseconds for a single prompt expands to 10 or 30 seconds as the agent deliberates. This reveals the hidden economic trap of the process: quadratic growth. We are looking at the agent's thinking budget. By the third iteration of a reflection loop, the model pays to reread the entire history of previous turns, plus the new context. The compute cost compounds with every cycle. Without dynamic turn limits or a strict thinking budget to cut the agent off when success becomes statistically unlikely, an autonomous reasoning loop will quickly bankrupt an enterprise cloud account. A common engineering misconception is that securing a workflow requires binary hard blocks to instantly kill a process the moment an agent makes a mistake. Consider an AI assistant tasked with booking corporate travel. The agent attempts to book a hotel room for 15 guests, but the internal enterprise policy dictates a strict maximum of 10. Under a legacy approach, the system detects the violation, hard blocks the call, and cancels the workflow. The modern approach intercepts it, returning a guide directive to reduce the guest count to 10. The agent processes this, autonomously self-corrects, and transmits the new command. It completes the booking without the human user ever needing to step in. Hard blocks are still required for compliance rules, like handling regulated PCI data. PCI refers to the payment card industry security standards for protecting sensitive financial information. But for standard operational logic, runtime steering maintains the agent's autonomy while keeping it within strict policy boundaries. As these agentic systems scale into enterprise production, they create severe operational blind spots. When an agent succeeds, you have the final output, but the logic and the route it used to get there are often opaque. Traditional deterministic monitoring relies on tracking simple uptime and latency. These metrics are not sufficient when an agent's execution route shifts unpredictably between API calls. An API is the interface that allows different software systems to communicate. This requires a dedicated AI observability plane. The system must map execution graphs, trace the lineage of a prompt, and record every specific tool choice. Visibility allows engineers to drive down those quadratic costs. Engineers use prompt caching to store repetitive system instructions, which reduces input token costs by up to 90%. The final structural component is the vector database memory layer. It stores information mathematically, allowing searches based on meaning rather than keywords. When a query arrives, the system checks the database for successful execution plans. If found, it instantly bypasses the language model entirely. Retrieving a cached plan drops system latency to 300 milliseconds. AI observability and memory layers actively optimize the thinking budget, ensuring the autonomous system remains economically viable at scale. We have moved from an isolated language model, fortified by a tool gateway, optimized by a memory layer, and governed by active steering guardrails. Polymorphic agents, systems capable of dynamically changing their functionality to span diverse enterprise environments, rely on these structural constraints to operate securely. Attempting to solve probabilistic agent deviations by continually scaling up to massive models is a losing strategy that will eventually break a company's budget. Success in deploying autonomous agents depends on the rigorous engineering of the environment, rather than the raw intelligence of the models themselves.